Alrighty, lesson 3. So we're going to look at how we can represent vectors in an algebraic way so that we don't have to keep drawing these ridiculous head-to-tail diagrams every single time we want to add vectors. And then we'll see kind of what does addition, subtraction, and scalar multiplication look like in the algebraic sense instead of the geometric sense. So to get started, ooh, green, fun. We'll start with this vector u. So the way that we represent vectors algebraically is, remember, vectors don't have a location. They just have a magnitude, a size, and a direction. So we're going to pretend that that vector is starting at the origin of a Cartesian plane. And so we're always going to pretend that it's starting at the origin, and wherever it ends up is going to be some point. Say it's the point A, B. And that is how we're going to represent that vector. We're going to say u is AB. And you're going to say, Mr. Clement, that's a point, and then u is a vector. So what this is doing is we're representing that vector, and when I list a set of coordinates and I'm telling you it's a vector, so I have a vector symbol in front of it, I'm saying the vector that starts at the origin and ends at the point AB. So that's our kind of setup. So for the vector u, 3, 4, and the vector v, 1, 2, we're going to find u plus v, u minus v, 2u, and the magnitude of u. So again, these look like points, but I know that they're not points because of the context. I'm being told that they are vectors, so I have to consider them as the vector that starts at the origin and ends at 3, 4. So I'll draw this out for the first one. So 3, 4 is there. So that is the vector u. The vector v is 1, 2. So 1, 2. There's the vector v. And what we're going to first do is do u plus v. So what I have to do, if I'm thinking about the the geometric interpretation of addition, is I have to redraw vector v at the head of the vector over here so that they're head to tail. So again, kind of picture the origin now being there, go over 1, up 2 from there, and draw the vector v, and we get that vector there. Oops. I'm just trying to clean up my picture a bit. So there's the two vectors drawn head to tail. So u plus v will connect from the start, which is the origin, to the end, which is 4, 6. So u plus v would be the vector 4, 6. And what we've just shown, 3, 4, that was u, plus 1, 2, that was v, equals 4, 6. And isn't that really convenient? If you look, if you add the x's, you get this value. If you add the y's, you get this value. So the wonderful thing is we have these things that are vectors. We've decided that to add vectors, you draw them head to tail and connect from the start to the end. We've come up with this algebraic way. Well, I'm just going to represent this vector as the point it would end at if it started at the origin. And our geometric way of adding vectors is exactly what you would want it to be algebraically. In order to add vectors, we don't need to draw a picture. We add the x's, we add the y's, that's our new vector. So, same sort of idea. We're going to now draw 3, 4. We're going to draw u again. And we're going to prove that vector subtraction works in the exact same way. So for subtraction, we want to draw the vectors tail to tail. So luckily, that's them starting at the origin. And to do u minus v, we connect from v to u, from the second to the first. So that's this vector that goes from there to there. So there's u minus v. And then to figure out what vector that is, well, it's going from 1, it's going over 1, 2, and it's going up 1, it looks like. So it's the vector 2, 1. If I place that red arrow back at the origin, I'd end up at the point 2, 1. So 3, 4 minus 1, 2. is the vector, did I say 2? Oh no, it's 2, 2. It's going from, sorry. I knew that was wrong as soon as I started to write it out. It's going up 2. It's going from 2 to 4. So it's going over 2 and up 2. It's the vector 2, 2. There we go. And so we'll see subtraction works exactly the same way we'd want it to. You do 3 minus 1, the x is subtracted, the y is subtracted, and you get exactly what you would want for the answer. And that works both geometrically and algebraically, working and getting the exact same result. For C, we're going to do a scalar multiplication, so I'm going to go with the easy 2u. So a vector twice as long as u in the same direction. So there's 3, 4. So there's the vector u. If I wanted to do 2u, I could add on another u from there. So go over 3 and up 4 from there. And there's the vector. I should do it in a different color. Here's, ooh, that's super wide. Sorry. This is the vector 2u. And we see it is in fact ending at 6, 8. So what that's showing, 2 times the vector 3, 4 is the vector 6, 8. And guess what? It works kind of what you'd expect it to work, or how you'd want it to work anyway. You multiply each component by 2, and you get the new vector. So that's wonderful. And then we're just going to get the magnitude of the vector u as our last thing, so that's for C. So this was A, B, C. Sorry, for D, we want to do the magnitude of the vector u. So maybe I'll just zoom in on this picture. If I want this length, well, I'd maybe think about this right angle triangle, which is 3. Ooh. Three over, 4 up. So if I wanted the length of u, I'd do a squared plus b squared equals c squared. I'd do the square root of a squared plus b squared, which is the square root of 25, which is just 5. But the key thing here is the magnitude of the vector 3, 4. To get the magnitude of that, you do the square root of its x, its components squared, and add it together. So it's x and its y added together. That's sort of going to be our formula for magnitude of a vector. So all that goes to show that with this way to represent vectors, all the operations you'd want to do work exactly how you'd want them to work. And to get the size of a vector, you do the square root of its components squared and add it up. Oh yeah! So here's some practice, so you can try these on your own. So pause the video, try these examples, and then we will, well, unpause the video. I'm going to do them right now. So bed mass kind of still applies. We're going to do our scalar multiplications first. So that's going to become 12 and 8 at the start. Subtract 6 and negative 4 now. And then add 50 and 0. And then we can just do the operations with the x's first. So 12 take away 6 is 6, and then add 50, we get 56. 8 take away negative 4 is 12, and then add 0. So we should get the vector 56, 12 as a single vector equivalent to the following, to that expression. Okay, so the next one gives us a new definition. So we've got this vector u, which is 5 minus 10. And a unit vector is something that it's a vector with length 1. So we're trying to find the unit vector with the same direction as this vector. So if you don't want to change the direction, but we do want to change the size, what we can think of that as is a scalar multiplication. Remember, scalar multiplication stretches the vector but doesn't change its direction. And so this vector is much longer than 1. We're just going to try and shrink it down to 1. So I'm going to see how long that vector is. The magnitude of that vector is the square root of 5 squared plus negative 10 squared it'll work out to be, which is the square root of 125, which if you want to have a decimal, you could get a decimal at this point. But I'm going to leave it like that because, as always, I didn't bring a calculator with me when I left my classroom to make this video. So basically, this vector is that long. So if you want to shrink it down to be a length of 1, so if its length was 10, if I multiplied that by 1 over 10, I would get a new length of 1. If I stretched it by 1 over 10, something that was 10 long, I'd get my new length of 1. So in order to make a unit vector version of u, so there's a special symbol instead of an arrow. If it's going to be a unit vector, you draw a little hat. So if it's going to be length 1, you can draw a little hat instead of an arrow. And we're going to take 1 over the square root of 125 as a scalar and multiply it by that vector. And that'll keep the direction, but it'll make the size shrink down to 1 if we kind of divide it by its size. So we get the resulting vector 5 over root 125, negative 10 over root 125. And again, if you want to get a decimal version of those, you can get a decimal version of those. And this next one, so we're going to come up with, we'll turn this into a formula, but we'll use a picture once to figure it out. So we're going to find the vector AB, so the vector that goes from point A to point B, that connects the points. So now we're not thinking of these as vectors, we're thinking of them as points, the point 3, 5 and the point minus 2, 3. So I'll zoom into my picture. We want 3, 5, that's A, minus 2, 3, that's B, and I want the vector that connects A to B. So I want this vector. And I kind of have to think, well, if this vector moved down to the origin, where would it end up? So it is going down from 5 to 3. It's going down 2. And it's going from 3 to negative 2. So it's going left 5. I got that right, I believe. And so if I redrew that at the origin, I'd go down to left 5. That vector would end up there. So the vector A to B is negative 2, negative 5. That's the point that you'd end up at if you started at the origin. And so what we want to do now is be able to do this question without a picture. So I'll look at these starting answers. So I've written those backwards. Sorry about that. Negative 5 is the x. Negative 2 is the y. It has been a long day, apparently. Okay, that looks better. So now we're going to look at those starting coordinates and figure out how could we look at those starting coordinates for A, B, and get to those answers without drawing the picture. So if you look at it, it's sort of a rise and run thing. So you remember you're subtracting the y's, subtracting the x's to get your rise over run, right? So y2 minus y1 over x2 minus x1. And just to get the direction right, because direction here does matter, we did, to get negative 2, you're doing 3 minus 5 for the y's, and to get negative 5, you're doing negative 2 minus 3. So the vector A to B, the vector that connects A to B, would be B take away A, would be negative 2, 3 as a vector, taking away 3, 5 as a vector. So subtract the x's, subtract the y, but you do second point first and subtract the first point. That's going to be our formula. So with that in mind, I'd like you to start a formula sheet for vectors so that we can keep all the key formulas in one spot. These things I would add to it. So if the vector, so the magnitude of a vector is the square root of its components squared and added up. This is a sort of an idea that we've talked about, but I usually put it on a formula sheet. If two vectors are collinear or parallel, so collinear means the same thing as parallel, that means that one is a scalar multiple of the other. So if they have the same direction or the opposite direction, you can turn one into the other by multiplying by some scalar. And that's the idea that we used here to keep the direction the same, but change it to this different vector that has a length of 1 instead of a length of root 125. We multiplied by some scalar. So That's something that I want to keep in mind. A unit vector in the same direction of u is given by u, and then I multiplied by 1 over the magnitude of u, but you can think of that also as dividing by the magnitude of u. Same deal, but you are doing technically scalar multiplication when you're doing that. And then that last question that we just did, the vector connecting points A to point B is given by B minus A, second point minus first point. And then at some point we should go over properties of vector addition, because it is different than regular addition. There is this sort of geometric interpretation. It's different than just regular numbers. So whenever we introduce a new type of operation, it's good to check that the properties that we expect to be there are still there. So this one I've already kind of showed you with that parallelogram diagram, but vector addition is what's called commutative. It is the same forwards and backwards, whereas subtraction in both vector form and in regular numbers, not commutative. 3 minus 5 is different from 5 minus 3. The next property is called associative. So if you're adding up 3 vectors, you can first add up the first 2 and then tack on the third, or you can actually first add the second 2 and then add the first one. So that's called the associative property, meaning basically these first 2 combo together to say, you know what, if you've got stuff added up, you can add them up in whatever order you feel like. The next thing, and you can prove all of these with little pictures, but if you're multiplying a sum by a scalar, that scalar does kind of distribute through. So it's the same thing as if you multiply each of the parts by that scalar first. Another important thing is there is a such thing as a zero vector. So a zero vector is just any vector that has a magnitude of 0. And if the magnitude is 0, it doesn't really matter what the direction is because it's not going anywhere. But that vector exists, so that would be the vector 0, 0 in our case. And that becomes what's called the identity element for addition, meaning there is something that you can add to a vector and not change the vector. If you add 0, 0 to any vector, it doesn't change the vector. That's an important property of what's called vector spaces in general, or that makes vector addition work like addition, so that's nice. So just something to keep in mind. Scalar multiplication is also associative. If you're multiplying a vector by, say, 10, you could multiply it by 2, then 5, and get the same result as multiplying it by 10. Or you can multiply it by 5, then 2, doesn't matter. And then this is a distributive property as well, but it's the other one. So the first one we had vectors being added. Here we have scalars being added. And that's just what that's another way of saying if you're multiplying by 10, let's say, you could multiply by 3 and by 7 and then add up those 2 results and get the same vector as multiplying by 10. So again, they all have fancy names, but basically these properties are saying these new operations that we haven't dealt with before do behave in the way that you want them to behave. So just important to point these out, that they exist. Some consolidation for you to make a note about what this lesson was about, and then again right into the practice that you can work on in class.